Welcome to this truss analysis GSA tutorial video where you're going to learn how to build a simple truss model in GSA. In order to illustrate this process, we're going to follow an example which you can find in your truss analysis GSA tutorial handout. The first step in the process is to create a new file. So you can go to File, New. A window will pop up where you can populate relevant information to the project, even though this will not affect in any way the results of your analysis. So if you wish to populate this information, you can, but you do not have to. The next thing you'll need to do is to define the structure type and units. So for our example, we're dealing with a planar truss. It's a 2D truss. So we can select structure type plane, and for the units we're going to select kilonewton meters. Once you've specified the structure type and units, you can click on Finish. And when you're queried about the grid, you can essentially say no. It's asking whether you would like to change the grid to have an X and Y coordinate, so having the Y in elevation, but we're going to stick to the coordinates proposed in the handout, in which we have X in one direction and Z in the vertical, so you can say no. The first thing we need to do, now that we've created a new file, is to define the nodal geometry. So in order to do that, you can go to the gateway menu, which is this menu to the left hand side of the screen. You can go to nodes and you can go to coordinates. All you need to do here is essentially input the coordinates of the nodes that you need to use in your analysis. For the example that we're using, if you refer to the Truss Analysis GSA tutorial handout, in Table 1, these are defined for you for this specific example. So for node 1, we have coordinates 0, 0. For node 2, we have coordinates 5 and 0. For node 3, we have coordinates 10, 0. For node 4, 15, 0. Node 5, 10, and 5. And for node 6, 5, and 5. You can see that this has a similar layout to that of Excel. So if you actually had all these nodes in a table in Excel, you could simply copy them and paste them in directly in order to expedite the process. If we close this window, now what we can see is that we have little red dots at the locations where we've defined our nodes. In addition to that, if we wanted to display the node numbers, we can click on the label node dots or label node numbers, and we could see that these would be on display in the screen. The next step is to create the truss element. So in order to do that, you can click on Add Elements Sculpt tool, and once you click on that, you can essentially just connect the nodes that you previously defined, and this will create elements between the nodes. If you need a reference figure in order to know which nodes to connect, you can refer to figure 1. At the same way that we did for the nodes, we could also illustrate the node, the element numbers. So in order to do this, just click on Label Element Numbers. And one thing that we need to do now is modify all of these elements, which are assumed to be rigidly connected, to a bar type element. And in order to do that, what we can do is click on the Select Elements shortcut, select all of the elements, right click, modify selected elements, and in modify type of 1D element 2, we want to change from a beam, which as I mentioned will assume by default that all of the connections are rigid, to a bar element. By making this change, we ensure that elements will only be able to take tension and compression, which is our assumption in the case of a truss. So if we do OK, you'll notice that there's a slightly different color in the beam elements, and this denotes that they've been changed from a beam type to a bar type. What this does effectively is that at the joints, all these elements are essentially free to rotate, and therefore we're meeting the assumption or the definition of a truss, which is the same one that you're using in your hand calculations to solve the same problem. The next step in this process is to generate the supports. So in order to do that, from the gateway menu, you can go to nodes, and then you can go to restraints. And in order to know what nodes to define, you can either refer to the figure, or you can also refer to table 2. And if we go to table 2 in the handout, you'll see that the nodes that are restrained are node 1 and node 4. In node 1 we have a pin, therefore we're restraining movement in the x direction and in the z direction. And in node 4 we have a roller, so we're just restraining displacement in the z direction. The same way that we did with the nodes and with elements, we can also display the support condition. So in order to do that, you can click on label restraints, and you'll see that we have our pin defined to the left and our roller. You can see a Z, essentially meaning that displacement or movement in the Z direction, which is up and down, is restrained, so effectively creating a roller on the right support. The next thing we need to do is to define the load case. You can do that also from the gateway menu. You can go to cases and tasks and load case specification. I'm going to call this load case simply point load, because we know we're applying point loads at some of the nodes in our truss. And as a case type, you can essentially just leave it as undefined. Once that's complete, what we can actually do is create the nodal loads that we will be defining. Again, you can do this from the gateway menu. You can go to loading, you can go to nodal loading, and in nodal loads, if you double click, you can essentially find the relevant input information on table 3. And what we're doing is specifying which nodes will have this load applied to them. So in this case, we're looking at nodes 2 and 3. The load case is the one that we've just defined, so point loads. So load case 1. We're referring to the global axis and the set direction for the load application, because we want the loads to go down. And the value, because the unit convention of the nomenclature is a positive Z is up, and we want the forces to go down, is a value of -10. And the same way that we did with the nodes, with the elements, with the supports, we can also now illustrate and display the loads in a graphical view. And in order to do this, you can click on all load diagrams, and you can see that we have an arrow pointing downwards in both nodes 2 and in node 3. And if we wanted to display the values of loads that are being applied in these locations, you can click on select var annotation and just hover over the 2 arrows, and you'll see that it has a value of 10 going downward, and as I mentioned before, positive Z is going up. That's why we input a -10 in the table when we're defining the loads. The next step is to define the cross-section properties for the different elements, which we have not yet done. So in order to do this, you can go from the gateway menu, you can go to properties, section properties. If you right click on the first cell and go to wizard, a window will pop up, and we're going to call this section truss member. There are a number of predefined materials in GSA, and in this case we're going to use one of them. We're going to select steel. And in order to define the cross-section, which you can refer to in table 4, we're going to go to a rectangular definition method. And if you click on next, what we're going to do is input these dimensions in millimeters, but we actually want a hollow cross-section. So we require the depth, the width, the thickness of the sides, and the thickness of the top and the bottom. And if we refer to the table, We have 500 millimeters wide, 500 millimeters deep, 25 millimeter thickness in the sides, top and bottom. Once we're done with this, we can click next and finish. And similar to what we've done before, we could also visually check that that we've input the correct cross-section properties. So in order to do that, we can click on section display, and you can see that rather than having the thin lines that we had before, we actually have a cross-section associated with each one of these members. And if we spin around our model or rotate it by clicking on rotate, you will notice that you actually have the cross-section that you've defined in all of these elements. So this is something that you can visually check. Now we can return to our Y elevation, and we're going to eliminate the section display. We're also going to turn off the node display and the element number display and the loads. So at this point we're ready to analyze our truss. So all we need to do is click on Analyze All. And once the analysis of the model is complete, what we're interested in checking is the actual results, so the value of axial force in our members, as well as the reactions. So in order to illustrate the axial force, we can click on the axial force diagram, and we'll see the diagram drawn in all of the members. And the same way that we checked the value of the loads before, we can select for annotation and check what these values are in each one of the members. We can also scale these diagrams up or down in order to make it easier for us to read. And essentially, where we have a positive value, we have tension. Where we have a negative value, we have compression. You'll notice that there are some members in which we have a value of force in the order of e to the negative 9. This is a very, very, very small number. Essentially, it's a 0. If you don't like seeing it expressed in such a way, you can click on the numeric format, select decimal, 2 decimal places, and you'll see it as a 0 force member, which is what actually it is in this case. We can also display the reactions. So in order to do that, we can click on the reaction diagrams, and we can also select these for annotation if we're interested in finding what the reactions at the supports are. So at this point, you've essentially obtained all the relevant information for this truss example. Another way of illustrating the results, if it's something that you're interested in knowing, you can show them using contour plots. So you can click on contour settings. You can go to beam and spring element results, beam and spring forces and moments. We can select axial force, contours based on actual values, and click on apply. And essentially what we'll see is a contour plot where we have colors associated with different load values. So we can see from the key to the right that we go anywhere from minus 14.14 kilonewtons all the way to 10 kilonewtons, and in some cases we'll have members with 0 forces. In the same way that we annotated these before, we can hover over the different elements and it will tell us what value of load each one of these has. So that concludes this GSA tutorial on how to build and analyze a truss.